Good morning, everyone. With this presentation, I intend to give you a general idea of my PhD project. And my project is inserted in the context of syntactic accelerations applied to neutron particle non-classical transport theory. And besides developing a new syntactic acceleration, in P1 syntactic acceleration in my case, is also included in my project to do a Fourier convergence analysis of this P1 syntactic acceleration itself, and also of two previous methods developed by some of our colleagues. Here's just an overview of my presentation. I'll start with the context and main goals of my project, and talk a little bit about applications of the non-classical transport theory. In second section, I'll basically talk about some difference and similarities in terms of equation of the non-classical and classical version. And section 3, some numerical results that I already have. And timeline, a general timeline of my whole PhD course, and also a specific timeline of my activities here at OSU, and an augment in the last section. Some of us in our Brazilian research team make part of an internationalization program supported by CAPES, and this is the name of the project. And our Brazilian team, led by Professor Barros and Professor Alves Filho, has been contributing to the classical transport theory since 1997. And Professor Vasquez, besides working with the classical transport theory, he also does research on the non-classical transport theory. So one of the main reasons of this collaboration between American and Brazilian groups is to advance the non-classical transport theory based on knowledge already developed in the classical transport theory. Just to mention a few applications of the non-classical theory, transport theory, and for example, in pebble bed nuclear reactors, and in photons transport in atmospheric clouds. For transport problems on this kind of stochastic media, the positions of the scattering centers are correlated. Mathematically, this means that the macroscopic total cross-section is a function of the distance between collisions. And the classical approach can be too expensive in this kind of problems. And then the non-classical approach can be a good option. Here we have a simplified version of the linear Boltzmann equation, and in this case, steady state, monoenergetic, and with isotropic scattering. And our unknown here is psi, that is the angular flux, that is a function of the position vector x and the direction omega. Sigma t is the macroscopic total cross-section. C, the scattering ratio, and Q is the internal source. This is a balanced equation, with the left-hand side represents loss terms, streaming and collision terms, and the right-hand side represents gain terms in scattering source and internal source. Compared to the non-classical transport version, considering the same simplifications, we can see that we have similar terms here, except for this new independent variable s, that is the distance between collisions, and this new derivative here with respect to this s and this delta function. And I'm just showing in this third equation that the macroscopic total cross-section is related to a distribution function P of s. In summary, some of our colleagues has developed a spectral approach that turns the non-classical equation that I showed you before into this problem, considering slab geometry and azimuthal symmetry. And so in this case, in this process of this transformation, one of the steps is to consider a polynomial expansion for the non-classical angular flux. and being m the truncation order of this expansion. The first work in the subject has considered a source iteration method to solve this problem, and the results were according to what we were expecting, but the main issue is the computational cost. Because as in the classical transport theory, the source iteration methods are source iteration method is very slow in problems with high scattering and low absorption. In other words, more diffusive problems. And for this reason, some synthetic accelerations are developed in order to improve the computational efficiency, reducing the number of iterations to achieve convergence. And in this context, a second work was published considering a S2 synthetic acceleration. And this method was well succeeded since the computational efficiency had a huge improvement. And here in red are my original contributions. Applied a Fourier convergence analysis on these two methods already developed, SI and S2SA. Propose a P1 synthetic acceleration, a new synthetic acceleration, and apply the same Fourier methodology on it. Here I have some numerical results to illustrate what I was saying. And this is a common transport problem in slab geometry with 20 centimeters of length, macroscopic total cross-section of 1, internal source Q of 1 as well, and vacuum boundary conditions. This epsilon here is the convergence number, and we use that to establish the stopping criteria. This first column there, is the scattering ratio, and I consider some values for that. This problem is the same of a classical problem, because I'm assuming an exponential distribution function P of S, but I'm using the non-classical approach to solve this problem. This first set of columns is the number of iterations to achieve convergence in the SI method and S2SA, and later on I'll fill that third column there with my results for the number of iterations in this case. This second set of columns is the numerical spectral radius that I calculated based on a code that I had access. And in the third set, we have the analytical spectral radius that I calculated by using Fourier convergence analysis. And this is one of my original contributions, as I said before. And the third column will be filled when I finish the P1 synthetic acceleration to develop this method and apply the same Fourier methodology. And what really matters at this point is to notice that for the SI method, we have the spectral radius equals to C. Same result of classical transport theory. And when we have the C closer to 1, we can see that we need a higher number of iterations to achieve convergence. This is related to the spectral radius. Because in simple words, to determine if an iterative method will converge or not, we can calculate the spectral radius. This quantity needs to be between 0 and 1 to guarantee convergence. And the closer to 1, the slower the iterative method is. So because of that, when you have the C closer to 1, we have the spectral radius closer to 1 as well in the SI method, and then we need more iterations to achieve convergence. But when we are considering the S2SA, we can see that we considerably decrease the spectral radius, and because of this, we need a lower number of iterations to achieve convergence, in this case 17. Right? And I calculate this numerical spectral rate just to confirm my analytical results. And as you can see, the values are pretty close in all cases. Here is basically the same problem, except for this P of S, that in this case I'm actually considering a non-classical distribution function. And here I obtained the same result for the SI method. Spectral radius equals to C. This means that for the SI method, the spectral radius doesn't depend on P of S. But in the S2SA case, the spectral radius have changed a little bit. Has changed a little bit. That's it. Here I'm just showing a general timeline of my whole PhD course, and it is separated by semesters. And I have finished all the subjects and exams in Brazil, and now I'm basically working on my project in order to write the dissertation when I go back to Brazil. And this is the specific timeline of my activities here at OSU, and this time is separated by months. And as I was supposed to do, I finished the Fourier analysis applied to SI and S2SA, and now I'm developing the P1 synthetic acceleration, and when it's done, I'm going to apply the same Fourier methodology on it. And I would like to thank CAPS for the funding to do my research, and especially my advisors, Professor Ricardo Barros, and Dr. Silva, for all the support and help to come here, and thank you all for the attention.